Welcome to the lectures on stellar evolution. And in particular, I will be presenting about the evolution of massive stars. I will see some of you later in the breakout rooms, and Tyrone Woods, my co-lecturer, you will see in one of the other breakout sessions. So to get an idea about what we are actually talking about, let's start at the very beginning of the story. So this is an environment, a planetary nebula, where we think stars form, a stellar nursery, and this is also where massive stars form. And you can see some hotter bluish gas, maybe even some violet colors in that region up here. And so in this kind of nebula is where we expect that stars are forming. So they start forming from some very extended, thin, and initially cold cloud of gas. But that cloud of gas then starts contracting towards making stars. So we have this picture again down here in the bottom left corner. And what I show here is a diagram of central density on the x-axis and central temperature on the y-axis, both on a logarithmic scale. And what is shown here is two trajectories of how the central temperature and density of stars evolve. And yeah, you can see, so we start at the very bottom. At the bottom left is where the stars are born in this nebula. And then they start contracting basically towards higher central temperatures and densities. So that is the overall simple picture of stellar evolution. So you start somewhere from a very thin, not very dense cloud, and then you contract to higher temperatures and higher densities in the centers of the stars until you reach at the very bottom a point that leads to collapse of the star and a supernova explosion potentially, as we will see later. So that's the overall picture, but it is not really the whole story, because the whole story is that stars actually start evolving along this track, and then they stop, they pause for some time. And in particular here at this first point where the capital H is standing, this is where the stars do central hydrogen burning, and they stop there for about 90% of their entire lifetime. And then they start contracting after they finished burning hydrogen. They start burning helium, and during that phase, they spend more or less almost all of the rest of their lifetime, so some 10% of their lifetime. And after that, they, when the helium is depleted, they start contracting again. Then the next phase will be carbon burning. Again, they stop for some time, but it's a very brief time. We will later see it's a few hundred, maybe 1,000 years. And then they move onwards. Along the way, there would be neon burning, oxygen burning. That goes very quickly. And then we have silicon burning. And eventually, the star builds up a core of iron in its center that then will collapse to make a neutron star or black hole. And if you're lucky at that time, also a supernova comes out. And so this shows you for two trajectories, a 15 solar mass star, so initially born with 15 times the mass of the sun, and a 25 solar mass star, so a star initially 25 times the mass of the sun. And after that, so when you reach that end phase, then you see some event that, is a supernova, a very bright explosion. So you can see that here as this blue dot. And as I have been assured by astronomers, these supernovae are very easy to spot because there's always these white arrows pointing at them. So you can immediately tell what a supernova is. There's always a white arrow pointing at them in all the pictures that you'll see. Okay, so to understand now how the evolution of the stars actually proceeds, we need to understand the different nuclear burning stages that stars undergo. So this is what we want to do next, follow the nuclear burning stages and the different ways in which stars actually produce energy and so fuse light elements into heavy elements, because this is what sets the time scale for their evolution, as we have seen. And as we will later see, it also sets the structure of the stars, how this burning proceeds, in what ways it propagates through the star towards the final phases of the star's life. Okay, so this is now the first phase, hydrogen burning, and what I will show here is nuclear burning stages for a 20 solar mass star, so a star born initially with 20 times the mass of the sun, with a composition roughly comparable to that of the sun. So about solar composition. So we have a main fuel, which is hydrogen, and a main product, which is helium. There's also some secondary product, nitrogen-14, and we'll discuss a little bit how this comes about and what the meaning of that is. Typical burning temperature for this kind of star is of the order of 20 to 30 million Kelvin. So the unit here is 10 to 9 Kelvin, gigakelvin. And for 20 solar mass star, the lifetime of that hydrogen burning phase is about 10 million years. And what it basically does, hydrogen burning, is that four protons are burned into one helium-4. And it does that for the massive stars by the CNO cycle that we will discuss. For lighter stars, stars with less initial mass, it's a different process, the PP chains that fuse that hydrogen. And so it's not just for hydrogen coming together to make helium, but it's somewhat more complicated, and it varies how that is occurring, as we will see next. Okay, so the first we have here is hydrogen burning by the PP chains, and that is mostly relevant for low mass stars. It also does occur in more massive stars, but it is not as important there. And the way this proceeds is, let's look at the graphical version first. We have as these black dots, protons. Two protons come together and they release a positron and a electron neutrino and make a deuterium, so a hydrogen-2 atom during that fusion process. And it does involve a weak reaction. So one of these protons actually has to be converted to a neutron, and you create this lepton-antilepton pair coming out. And that's a process that is actually fairly slow and sets the time scale for how fast this hydrogen burning can actually go ahead. Then we have another reaction where this deuterium captures another proton and makes helium-3. And so from that point on, we actually have to wait for another helium-3 being made in the same way on this side. And then eventually, if you have made enough helium-3, some of these may eventually find each other and can fuse together and make a helium-4. So this part over here. And as you when you count, okay, there's actually six nucleons coming in. And so there's each of these has 2 protons and 1 neutron, and the helium-4 has 2 protons and 2 neutrons. So 2 of the protons are superfluous and are being released again, and so they can go back to the beginning of the cycle. So to some extent, if you so will, the protons are actually self-catalyzing their burning to a helium. So because some of them are coming back out and are going in at some point, but just come out. So they catalyze the process there, come out unchanged from that cycle. But eventually they are being used up as well. So there is an alternative way that can happen. So instead of 2 helium-3 coming together making a helium-4, one of these helium-3 could also react with a helium-4 nucleus, and that would make a beryllium-7. And this beryllium-7 has now 2 possible ways how it can continue. So the first way, unfortunately here to the right-hand side, is that it could capture an electron, releasing a neutrino and making lithium-7. And this lithium-7 can then capture another proton, and then you have principally a beryllium-8, but that is extremely short-lived and decays back into 2 alpha particles, or it's more or less a direct reaction. The proton comes in and 2 alphas come out. So a p-alpha reaction on the lithium-7. And there's a third way of how this can proceed, and that is if instead of an electron being captured, depending on the time scale and temperature of your environment, or the time scale that is set by the temperature of your environment, I should say, you could have also a proton capture on this beryllium-7 at somewhat higher temperatures. And when this happens, then you make a boron-8, and that boron-8 can decay, emitting a positron and an electron neutrino, making beryllium-8, which then again decays into 2 alpha particles. So you have basically 3 different ways of making that, and they are accordingly called the PP1, PP2, and PP3 chain, because you always have to start at some point at least to get 2 protons come together and convert a proton into a neutron that is required. Then you have your helium-3, and then you basically use for the PP2 and 3 chains, you use one of these helium-4 to catalyze the burning of this helium-3, at some point adding an extra proton and having another decay, and then make another helium-4 come out. So for the PP1 chain, basically the proton self-catalyze, and for the PP2 and PP3 chains, it is actually a helium that catalyzes the burning of hydrogen to helium. Here's also another way of looking at it. Maybe it's simpler, it's just not so graphically beautiful. So we have the same reactions lined up here, and then you have this branching point, either 2 helium-3 come together and you make the helium-4 directly, releasing protons, PP1, or the helium-3 that you make in this first step process captures a helium-4, making beryllium-7, and then you have these 2 possibilities, either electron capture or proton capture, and then proceeding to eventually make another helium nucleus. There's also an interesting aspect to that, namely that depending on which of these paths you take, you will release different amounts of energy. And how is this possible? Because what all of these reactions do is that they convert 4 protons into a helium-4. So you have all of these have the same amount of or the same input and output, but they deposit different amounts of energy inside our star. So maybe energy release is not quite the right way of putting it. What is meant is the amount of energy that deposit in the star. So how can this come about? Maybe think for a minute. What might be different between these different processes to allow that to happen? Well, what is different between the different processes is that we make neutrinos at different reactions. And it is these neutrinos that basically don't interact with your star. They can travel through stellar matter for very long distances without any interaction, so they escape from where they're made. But the energy of neutrinos that, or the energy, of the neutrinos that you make will vary. It will be different between these this first reaction up here, between the second and the third reaction. So this is why you have different energies deposited in the star, because the neutrinos carry away different amounts of energies in these different reactions. So this is what causes this difference. I should also add that, okay, when do you actually expect to have which of these processes to occur. It does depend on temperature. Namely, if you have higher temperature, it's easier to overcome larger Coulomb barriers, and you have only helium and particles and protons coming together. Here you make already lithium, and here you even go all the way to beryllium. So you will find typically the pp1 chain at lowest temperatures, and at higher temperatures you start setting in the pp2 chain, and at even higher temperatures you would see the pp3 chain setting in. But overall, the reactions are dominate, or what has to happen in any case is this first part of these reactions, or this H proton plus proton, have to come together to make your deuterium, and then that has to burn to make helium-3. So that's unavoidable. It's required for all of these three reactions, and that's a very slow rate, and sets the time scale for the entire pp chains to be roughly of the order or scale with temperature to the 4th power. So that already sounds or seems quite a bit, but we will see later that it's actually a very low scaling. Many of the other reactions are much more temperature sensitive than this. So it is really almost temperature insensitive, if you so will, compared to how steeply temperature sensitive other reactions are. Okay, so this is happens or mostly plays a role in low mass stars. If we go to higher mass stars, we have hydrogen burning by the CNO cycle. And so that is a lot more complicated. There is actually, well, here I write as a CNO bicycle, but there's even higher cycles, CNO3 cycle and so forth, that can go on, involving even heavier nuclei than what is shown here. But this is really the dominant part of the cycle. The other cycles mostly feed into the cycle in the end as they occur. So what is that main cycle? We have carbon-12 capturing a proton, making nitrogen-13, which is radioactive. And so it decays, making carbon-13 and releasing positron and neutrino. So again, here we lose some energy. Then next is this carbon-13 can capture another proton, making nitrogen-14, releasing some energy. Then that nitrogen-14 can capture another proton, making oxygen-15, which is radioactive and decays to nitrogen-15. And then this nitrogen-15 can capture another proton. And at that point, there is a potential branching, namely either it can make a compound nucleus decaying, releasing an alpha particle. And so then this is where we want to get. And you make a carbon-12, and we are then back at the beginning of our cycle. So what we have made in total is we had here 1 proton, 2 proton, 3 proton, 4 proton go in, and 1 helium-4 come out. And along the way, we had also 2 positrons and 2 electron neutrinos come out. So the same as what the pp chains do, except that you have these heavier nuclei involved. And what this implies is because they have a nuclei, you require higher temperatures to overcome the Coulomb barrier. So yeah, then is here this magical branching that you can also see. It turns out the ratio of branching is about 1 to 10,000. So in only in 1 out of 10,000 cases, you will make this other branch and de-excite to release a oxygen-16 instead of particle emission. And then that oxygen-16 can capture another proton, making fluorine-17, which is radioactive and decays to oxygen-17. And then that oxygen-17 can capture a proton and make nitrogen-14 and release an alpha particle. And with this nitrogen-14, we go back here in our main cycle. And of course, there's also other branchings that can happen. For example, you could not emit the alpha particle and make instead fluorine-18 and can decay. And then would you have a breakout from that cycle and have a third CNO cycle that eventually feeds back into the main cycle. But these are usually low branchings, and these are the dominant ones. And The reason why we show this cycle in the first place is that the oxygen-16 is usually the most abundant of the CNO elements. And what that CNO2 cycle does for the most part is that it leads to conversion of the oxygen-16 into some nuclei that can participate in the main cycle. And so once you're in the main cycle, you mostly remain in that because the branching out or the side branch is very, very weak, only 1 in 10,000 that it will go into that cycle. And it can be important if there's a significant leakage from the cycle this way, but at lower temperatures, that is not happening at a significant rate. And so you may mostly stay trapped inside that main cycle. So from that cycle, you have some energy release or deposition in the star, that is 24.97 MeV. So you have, again, some of the energy is carried away in form of neutrinos. It's different from what you had released or the energies in the neutrinos from the PP cycles. And the reaction rate has typically now a temperature sensitivity of T temperature to the power 16 compared to T to the power 4 that we had seen for the PP chains. So when you look at that cycle, we might also wonder, okay, you make some radiative decays, some radiative particles, but some of them may be long-lived. But that is actually not the case. So all of this can proceed fairly fast. And so I have written these out here, how long these beta decays take. So for oxygen 14, we will see this a little bit later, with 70 seconds. Oxygen 15 that played a role here was 122 seconds. Nitrogen 13 is 10 minutes. Fluorine 17 is 64 seconds. One we hadn't seen yet, but it can play a role in one of the other CNO cycles. Oxygen 18 lives almost 2 hours. So we see from that, okay, this is minutes, of the order of minutes, maybe hours in some rare cases that it takes for the radiative decays, and that has to be compared to the lifetime of the star, which for the sun is 10 billion years, or for our massive stars that we looked at is 10 billion years. So these are very, very short times, basically negligible times. And when we look at the cycle, there's also a peculiarity about it, namely that this reaction of the proton capture on nitrogen 14 to oxygen 15 is usually the slowest of these reactions, the lowest cross sections. So that means you run through your cycle, and so let's go one slide back. So you would run through your cycle somewhere up here, and then around and round, and then you get to your nitrogen 14, and there you get stuck, and then you have to wait for this proton capture to occur. And so that means that you start piling up material in nitrogen 14. And so that is why it's important, and you remember from our summary slide that we said, oh, a side product is nitrogen 14, and that is because this reaction here is a bottleneck. So even your oxygen 16, which is the most abundant of the CNO elements, and all the others as well, they mostly end up as nitrogen 14 as the dominant product. And so when you reach the end of hydrogen burning, you will expect to see, you have mostly helium, and the second most abundant element that you would have in your star is nitrogen 14, because of all of these elements are converted to nitrogen 14. Oxygen was before that, it was the most abundant element after hydrogen and helium, and the hydrogen has burned out, because that's what we do, hydrogen burning. So we are only left from the residual of this oxygen 16, which ends up in nitrogen 14 for the massive stars. So that means most of the CNO cycle elements are converted into nitrogen 14 because it is a bottleneck. Then we had these different temperature sensitivities that I mentioned. So we have the PP chain, and I plot here logarithm of temperature for the burning, and here the logarithm of the energy generation rate, specific energy generation rate in ergs per gram and second on the y-axis. And because of these different slopes, so here's for the PP chain, and because the CNO cycle has this much higher temperature sensitivity, it is very unimportant at low temperatures, but as temperature rises, it becomes faster, more important, and at some point there's a crossover that is very close to the central temperature of the sun, where the CNO cycle starts to take over and become the dominant reaction rate. And so one has to look at that in the perspective that stars, as they get more massive, will have higher central temperatures. So low mass stars will have lower central temperatures, and they will be dominated by the PP chains. And high mass stars have higher central temperatures, and they will be therefore dominated by the energy generation, hydrogen burning by the CNO cycle. It doesn't mean that the hydrogen burning by the PP chain doesn't occur. It just means that it is not a dominant process, because the other process by the CNO cycle is more important easily by orders of magnitude. There's also something else that can happen as we reach higher temperatures. So here we have our cycle that we just looked at, the CNO cycle. Yeah, what we have here is, okay, we have the proton capture, decay, capture, and then we have this very slow capture of a proton onto nitrogen 14, making oxygen 15, we have decay, and then we have this other reaction that gets us back to carbon 12. And I only show the CNO 1 cycle here. But as temperature gets higher, these proton captures get faster and faster. And at some point, you can have also proton capture at the nitrogen 14 becoming faster than this beta decay. And so instead of beta decaying, it will move onwards to make the next nuclei, another proton capture, getting to oxygen 14, which then decays. And then from there, you can go oxygen 15, decay, and then we have the regular closure of the cycle. You can't have any additional proton captures up here because the next nucleus up would be proton unbound. So basically, the proton doesn't stick, it comes back out. So you're stuck here. And so, as we said, these proton captures are now faster than our beta decays, but still you're stuck in this nucleus. And so you have to wait for this beta decay. And they always, more or less, at these relevant temperatures happen at the same temperature. So they are fairly temperature insensitive in the relevant temperature range here. And so you have to wait here for your 70 seconds to decay, and you make the oxygen 15, and you have to wait for your 122 seconds for the oxygen 15 decay. And so in that case, that is what sets the time scale. But of course, the time scale is not very long. As we said, it's 70 seconds and 122 seconds. So basically in 3 minutes, you can do 1 cycle. And now you can do an estimate. So you know how much hydrogen you have initially in your star, which is about 70% hydrogen by mass fraction. And you have maybe 1% of CNO material by mass fraction. So you can compute how many of these nuclei you have. And you know that 1 cycle takes about 3 minutes, and it burns 4 protons at the helium-4. So you can make a rough estimate how long it would take by this process to burn all of your hydrogen to helium. And it's of the order of a few hours, so 10 hours, depending on what exactly your metallicity is in CNO fraction and the hydrogen that you have. But so it can go very fast. So for a star, for like the sun, hydrogen burning, well, it goes by the PP chain and takes 10 billion years. For our 20 solar mass star, it goes by the CNO cycle. It takes 10 million years to burn. So this process gets, because of its high temperature sensitivity, gets much faster. But eventually, if you have in conditions where temperature is very high, it can go as fast as a few hours. And this is something that we would, for example, see at the surfaces of accreting neutron stars. They have very high temperatures, high densities, and then any kind of material you dump on top of your neutron star would burn for solar composition in a matter of a few hours to helium. Okay. So we have now seen this part. So the next that happens helium burning. So again, we recapitulate: hydrogen burns the helium and makes nitrogen-14 as a secondary product. Happens at around 20 to 30 million Kelvin, takes 10 million years for our 20 solar mass star. And for these massive stars, it's 4 hydrogen burning to helium, but it goes by the CNO cycle. So that's the most complicated of this burning process is the light end. The next burning phase is helium burning to carbon and oxygen, and it does make a side products oxygen 18 and neon 22. And the typical temperature of that is about 200 to 300 million Kelvin, and the time scale is now down by a factor 10 to about 1 million years. And there's 2 different competing reactions that use up your helium 4, and so one is fusing 3 helium 4s together to make carbon 12, and another is capturing one of these helium 4 as an alpha particle on carbon 12 to make the oxygen 16. So how does that look in detail? Here's the process. So you have 2 helium 4 interact. They can make a beryllium 8, but that is extremely short-lived, 10 to minus a few times 10 to minus 16 seconds. So you make some, it will decay. You build up a very low equilibrium abundance of this beryllium 8. It can capture another alpha particle sometimes on top of that, but if you do this, then it can de-excite, emitting a photon, and make carbon 12. So this is a 2-step process. You first make equilibrium abundance beryllium 8, and then capture another alpha particle and make carbon 12. And the energy release there is now of the order of 7 MeV in total. So that is, you have 12 nucleons involved, you make 7 MeV per nucleon. So you get of the order of 0.6 MeV per nucleon. And that is compared to hydrogen burning. Maybe if you recall, we had something like peak 26, up to 26 mega electron volts for 4 particles. So there you have more than 6.5 MeV per nucleon. And here I have 0.6 MeV per nucleon. So the energy release per unit mass is about 10 times less for your helium burning than you had for the hydrogen burning. And that also explains why you have about 10 times shorter lifetime. So if your star has a comparable luminosity, but the energy source is 10 times less efficient, then your energy source will also only last 10 times shorter at the same luminosity of your star. And so, so it's a direct relation between the energy that is being released by the burning compared to your lifetime. So it directly relates between the lifetime and the energy release for a given luminosity. This process has now, it scales with density squared because 3 particles have to come together, and it has a very high temperature sensitivity of T to power 40. So once the helium burning starts, it sets in rapidly and saturates quickly. So usually it burns at very similar temperatures because of this high temperature sensitivity. And you can have more extended picture, namely once you have made this carbon 12, you can actually have another alpha particle capture and make oxygen 16. It may be hard to read in here. So the way we can envision this, we have an alpha particle and we capture another alpha particle on this, make beryllium 8, costs some energy, we capture yet another alpha particle, and then we can de-excite into carbon 12. And then from the carbon 12, if we capture an alpha particle, we get down to oxygen 16. And you can already see this here roughly. What is quite remarkable is that, okay, it's the energy difference that you go down here, which is about the same between from our 3 alpha particles making 1 carbon 12, and then from carbon 12 to oxygen 16, you release about the same amount of energy than from making the carbon. So making the oxygen 16 is much more energy efficient if you want, by releasing more energy per alpha particle than making the initial carbon-12. Okay. So I'll put this on the slide. So we have the oxygen production, helium-4 plus carbon-12 makes the oxygen-16. And again, you see, again, we make about 7 MeV in total, but we use up only 1 alpha particle to make the same amount of energy than we made for the we released for the carbon-12. And that process has a similar temperature sensitivity of the order of temperature to power 40, but it has a lower density sensitivity. And the final abundance or ratio that you see of carbon to oxygen is then set by a competition of this triple alpha reaction and the carbon-12 alpha gamma reaction. And that is yeah, but this oxygen-16 production can only actually start after you started having made some carbon. And so this here is kind of a not great plot because of some numerics, but it gives you the rough picture. So what I plot here is a function of time evolution of a typical star, a massive star, where we start off with almost 100% helium-4. You recall there was a little bit of material that was in our nitrogen 14. So that's being burned, it's used up, and initially you burn it to make carbon, but once you start making a noticeable amount of carbon, you also are able to capture alpha particles to make oxygen-16. And then so in the end, somewhere around this point here, you start making, you convert more carbon to oxygen, then you are able to make new carbon. And so then the carbon curve starts declining and the oxygen curve starts rising up. If we assume the star has about a comparable luminosity, and we recall that the energy release from alpha particles capturing on carbon is much more efficient to make your oxygen-16 than making carbon, is that you require less alpha particles to produce the same amount of energy. And so that curve of our helium abundance, so the helium abundance drops somewhat less fast or more slowly. So it becomes somewhat shallower, at least with a little bit of goodwill. You can see that it's steeper initially and somewhat shallower at the end. And that's because you release more energy per alpha particle at the end of your helium burning phase, when you mostly make oxygen-16 rather than making carbon-12. So all of this, what you make here will sensitively depend on the actual reaction rates that you have for this. As I said, it's a competition between the triple alpha rate and the C12 alpha gamma rate. So here's a plot where we started to actually modify these, just because some of you might be interested in measuring these rates. I'll show you this. So this is our standard rate at 1, and also here standard multiplier, some in the middle on the x-axis and on the y-axis. And this shows as color coding the carbon mass fraction that you have at the end of helium burning for different stellar masses, so 12, 13, 14, 15, and so forth, up to 30 solar mass stars. And for varying the carbon-12 alpha gamma rate and this triple alpha rate. So obviously, when the relation between these rates is reasonably straightforward to understand. Obviously, if the triple alpha rate is faster, so it makes easier carbon, you will end up with more carbon. And if the C12 alpha gamma rate is faster, you destroy more carbon, so you end up with less carbon. This is what you will see when you go in this direction. So if you have low production of carbon, by triple alpha and large destruction by C12 alpha gamma, you make the least amount of carbon, and vice versa. You make the most when it's rigged the other way. So you have the least destruction and the most production. But it's also interesting to see is that there's some sensitivity also with the stellar mass, because these lower mass stars have typically lower temperatures and higher densities, and the higher densities then favor more of the production of carbon-12, because you have a temperature density sensitivity rho squared for the production, but only a single density sensitivity for the destruction by C12 alpha gamma. So these more dense stars of lower mass, they tend to make more carbon-12 than the high mass stars of low density. Okay. So, so this was our helium burning, making carbon and oxygen by these two processes. We have seen there is a secondary production of oxygen 18 and neon 22, and that is actually being made out of nitrogen 14. So also this one can capture an alpha particle to make oxygen 18. So it first goes to neon 18, decays to oxygen 18, and then you can have another alpha capture to make neon 22. And then later, this neon 22, towards the end of helium burning, it can actually capture yet another alpha particle and release a neutron. And these can be used to build up heavy elements starting at iron. Oh, sorry, it makes nitrogen, fluorine 18, and that decays to oxygen 18. Okay. Not neon 18. Okay. So the next is then we have carbon burning, and carbon burning makes as main product neon and magnesium. And there is also a side product you make, maybe a little bit of sodium along the way. The burning temperature is of the order of 800 million to maybe 1 billion Kelvin, and the time scale is reduced by a factor 1,000. So it only lasts about a few hundred to maybe 1,000 years. And the main reaction is carbon-12 plus carbon-12 is coming together. So that seems quite a remarkable change. Does it really release 1,000 times less energy? Well, we will see that in 1 or 2 slides down. What's the reason for that? So first, what is the reaction? So let's first just look at carbon burning here on top. We will look at oxygen burning later. So what happens is 2 carbon come together. In principle, there's a way that it could de-excite to make magnesium 24, but it's a very rare, very small branching ratio for this. The dominant branching ratios is that it would magnesium 23 and a neutron, or it makes sodium 23 and a proton, and maybe also neon 20 and the alpha particle. In somewhat more rare cases, it might also make oxygen 16 and 2 alpha particles. So this one here makes 13.9 MeV, and then these other, so these dominant branches here, they maybe some of them even cost energy, some produce a little bit of energy, but after the carbon burning is over, we actually get an average energy of 13 MeV out. That is kind of confusing. What's going on here? So let's let you think about this for a few seconds. How can this be that we have actually an average that is so much higher than what is actually coming from the dominant rates? So what is going on here is that, well, you don't just make magnesium 23 and the neutron, but the neutron and proton alpha particles that you make here, these are particles that have sort of a high energy content, in the sense that when they can react with other nuclei and release a lot of energy in that reaction. And so this is where you get this extra energy from. So you have the secondary particles, and they can react onward. Magnesium 23, for example, can also decay to sodium 23. And these neutrons and protons, they can capture on other nuclei, often going back to making magnesium. 24 in some kind of indirect way. And that releases a lot of this extra energy so that we end up, including the secondary particle reactions, about 13 MeV per nucleon. So now the other question is what's the low time scale? Because, okay, when you now really look at that, we have 24 mass units, atomic mass units, and make 13 MeV. So that gives of the order of 0.5 MeV per nucleon. So that's not too different from the 0.6 MeV per nucleon that we had from helium burning, but yet the time scale was 1,000 times shorter. So what's really going on here? Well, one explanation is, well, maybe we don't have 100% helium, we have only some fraction of carbon, but that fraction of carbon was 30 to 50% or so. So it's not a factor 1,000 different. Or we don't burn all of it. Well, we do burn all of it. So that's also not what can happen. Well, what happens is that the star starts getting hot enough at around 1 billion Kelvin that photons can make electron-positron pairs. And usually what these electron-positron pairs do is that they annihilate again to make again two photons coming back out. But not always. Sometimes these photons, when they come together, they can actually make neutrino-antineutrino pairs. And again, similar to what we had for the hydrogen burning, is that our neutrinos are escaping and therefore we are losing energy. We also have this process that just happens in the plasma of the gas that leads to some loss of energy from making neutrinos or neutrino-antineutrino pairs that directly escape from the star without interacting. And this actually has a very high sensitivity to temperature as well. So this energy loss due to neutrinos is scales with temperature to the 9th power or even higher power. Depends on the detailed process that dominates. This is only one of the processes that happen. There's other processes as well that can start producing neutrinos and that are then being lost. And these are very volatile particles. Escaping from the star very easy, but for some cases one can actually see them. For example, one can see the sun in neutrinos. Here a picture from Kamiokande, although the angle resolution is not very great, so the sun is probably only a small fraction here, and it is not these pair neutrinos that we see from the sun. You may recall the neutrinos that are coming from the sun are actually those from the PP chains and maybe a little bit contribution from the CNO, from the CNO cycle, but mostly from the PP chains. But in principle, if you had a star close by enough shining in neutrinos, then you might be able to see it. Now, for our star doing the carbon burning, that becomes quite a significant loss. And so when we know it's about the same amount of energy being released on one hand, but the time scale is down by a factor 1,000. So that tells us, well, we must be losing basically 1,000 times more energy in form of neutrinos than we lose in form of photons that make our star shine from the outside. So what it basically means is that at this point, our star is no longer a photon star, it is now a neutrino star. So the star starts shining brighter in neutrinos once you enter that phase of carbon burning, but it's we already see, okay, it's a very short phase in which that dominates for the stars. And these lifetimes are so short, not because there's not that much energy, but it's because all this energy is escaping, it's leaking away in a different form, in the form of neutrinos. Okay. So then the next phase that we have is neon burning. So yes, I'm a little bit out of order. Neon is burning to making oxygen and magnesium, and you can have some side products, aluminum and phosphorus. The typical temperature of that is 1.5 billion Kelvin, and the time scale is now down to something of the order of a few years. And there's actually, it's a complicated process that how neon burns in its unique way. We will look at that on the next slide. Okay. So what happens for neon burning is that it doesn't do the same thing as carbon does, namely two neon just coming together and making a reaction. No, but instead what happens is that you have a combination of a photodisintegration reaction and an alpha capture. So the first step, what happens is that a high energetic photon knocks out a alpha particle from the neon and you get an oxygen 16 and the alpha particle, and it actually costs energy. It costs a lot of energy, minus 4.73 MeV. It dominates over the inverse reaction for a temperature above about 1.5 billion Kelvin. But then this alpha particle, it can actually capture on another neon 20 nucleus, namely neon 20 plus alpha makes magnesium 24. And so then you have effectively burned two of the neons with the photon coming in into an oxygen 16 and a magnesium 24. And yeah, this here releases a lot of energy, more than 9 MeV. I didn't have the numbers here in detail. But the total of both reactions is plus 4.5 MeV of energy. So despite the first reaction cost you some energy, the second one you get sufficient energy out to make this an exertic process. It's not quite as efficient as our carbon burning, so you have 40 nucleons involved and get 4 MeV out. So you get something of the order of 0.11 MeV per nucleon out from this reaction. So it's not that effective, efficient, but it still releases a lot of energy. And because of it's only a single particle reaction, it tends to be, as we will later see, kind of flashy, happens very fast. Okay. So we have this very peculiar reaction. The next one is oxygen burning to silicon and sulfur, making side products, also chlorine, argon, potassium, calcium. The burning temperature now is 2 to 2.5 billion Kelvin, and the time scale is now down to a year. And we have this further reaction time scales just because of higher temperatures. The neutrino losses that have this high temperature sensitivity of T to the power 9 or more carry away more and more energy. And for the neon burning, there's not really a lot of fuel available, so there's not that much neon, but oxygen is quite abundant when it starts burning, so it burns somewhat longer than your neon burning. But again, it's still short. It's usually less, a year or less for the oxygen burning. And the reaction there is very similar to the carbon burning. We've seen this on the previous slide. So very similar to the carbon burning. Again, we have two oxygen come together. They make sulfur 32 in principle, but it's not a dominant branch. More common are branches to make a proton, neutron, or alpha particle, maybe even two alpha particles. And we have, again, the same relation that the first step of the reaction where you de-excite your nucleus by emission of particles only releases some fraction of the energy, but then these particles can make secondary reactions that in total release a significant amount of energy. And again, we see here, okay, we have 16 plus 16, 32 mass units going in and 16 MeV coming out. So again, we have about half an MeV per nucleon, so similar to the carbon burning for our oxygen burning. Okay, so then last but not least, we have silicon and sulfur that we made by this process burning to iron. And there's some other iron group elements that we make along the way. The typical temperature for that is 3.5 billion Kelvin. And the time scale is now as short as 0.02 years. So that's about a week. So this final phase of stellar evolution really only takes about a week to proceed. And that proceeds in a way that is sort of similar to the neon burning, except that it goes in a much more extended way. You kind of carry that to the extreme. So you basically have a whole sequence of gamma alpha and alpha gamma reactions to disassemble some of the sulfur and silicon and build up eventually iron or iron group elements. And along the line, you start reaching temperatures and densities where you also have increasingly more weak reactions, that is converting some of these protons to more neutrons by electron captures. And so you start making a more neutron-rich iron core at the end of silicon burning. And then once you get to the point after all the silicon is being burned, you're typically in an environment where the reactions between the nuclei go extremely fast. So we are in a state that is referred to as nuclear statistical equilibrium. In principle, what you would call an equilibrium just depends on the time scale and at which you're looking at. So in this case, the time scale for the nuclear reactions between the different nuclei are much, much shorter than the characteristic evolution time of the star. So this is in contrast to what you have in early evolution stages, where the dynamical and hydrodynamic time scales of the star are much shorter than the characteristic burning time scales. But here in this last phase, at these high temperatures, nuclei can react very quickly, and they find a kind of optimal distribution of different species that you find in your star. So this shows you what the distribution actually is that you would have for different nuclei as log of abundances on the y-axis as a function of how neutron-rich your material already is. So this 0 would be equal number of neutrons and protons. So the most stable nucleus is nickel 56. But as you have weak reactions and get more neutron-rich, you start building up different nuclei that could in principle live in your star. It depends a little bit how large the density also is to have more electron captures because of degeneracy. Okay. And yeah, so similar to ionization stages in atoms, it's again, you can use Saha equation to determine exactly what the distribution is that you should expect for a given neutron enrichment, that is for a given neutron to proton ratio, what kind of nuclei you might find. So to summarize, we had here these different processes. Hydrogen burned by the pp chain, so by the CNO cycle, and you have some threshold for the burning. You make helium, and the energy release that you get from these different ways of burning is slightly different between the pp chains and the CNO cycle. Then helium burning gives you of the order of 0.6 MeV per nucleon. Carbon oxygen burning, both of them of the order of 0.5, 0.3 MeV, depending on what exactly the products are. Neon burning was not listed here, but we recall it was of the order of 0.1 MeV per nucleon, and that's final phase silicon and sulfur burning into some nuclear equilibrium processes, alpha, gamma, gamma alpha reactions to the iron group gives you about of the order of 0.2 MeV per nucleon. In some stars, when you have enough nitrogen present, for example, very metal-rich stars, you can have this phase of nitrogen burning. For less metal-rich stars, it happens just in this transition phase between the end of hydrogen burning and the beginning of helium burning. So you remember that nitrogen-14 was made as the slowest reactant in the CNO cycle, but at the onset of helium burning, it actually starts burning before much of the helium is burning, and you have a capture of alpha particle nitrogen-14, making fluorine 18, that is radioactive decays, making oxygen 18, which can capture another alpha particle, making neon 22. So all of this nitrogen 14 was not there present initially in the star, but was made in the CNO cycle. But for metal-rich stars, say something that has few times, several times, 10 times the metallicity of the sun, it actually can develop into its own short burning phase that you can see at the transition between hydrogen burning and helium burning. It might even take up a few percent of the lifetime of the star, or a few percent of the helium burning time of the star, depending on how much of it there is. Okay, so this was our summary. We had these different burning phases: hydrogen burning to helium, helium burning carbon, oxygen, then carbon making neon, magnesium, neon gets to oxygen, magnesium, then we burn oxygen to silicon sulfur, and finally silicon sulfur to iron. And what item to remember is that despite oxygen is actually lighter than the neon, it does burn second because it's a double magic nucleus, so it's kind of inert in the reaction. But the neon, you start disassemble first into oxygen 16 and magnesium. Okay, so let's take a quick break here. That's the first section of this lecture.